Okay, so I'll start with the session. So this session today is all about a guide to applied machine learning. We all have been reading and knowing that machine learning is something that is prevalent today in almost all the fields, but a lot of focus is on a theoretical machine learning, on understanding different models and how we can use different kinds of data sets. And we practice mostly on notebooks and Kaggles, but less focus has been given on making sure how we can actually apply this machine learning to real world business use cases. So this webinar will mostly be focused on applied part of machine learning, where we will not go into details on the algorithms that are there, but we will try to understand that how we can actually use those algorithms in different business industries and apply them to actual real world production cases. So the agenda today will be, in a very brief note, understanding what machine learning is, what are the different types of machine learning, what are the different various applications of machine learning, deep learning, and how we can go ahead with productionizing these different machine learning solutions. Because we understand that there have been a lot of development in different forms of machine learning algorithms, but very few of them are actually being used in production today. There's so much scope of applying these machine learning algorithms to a lot of different use cases. We'll go through detail, and then we'll also do some hands-on on understanding how maybe we can start with a simple algorithm and how we can go ahead and try tracking it in the real world scenario, and then we can try on different kinds of algorithms and experiment to understand which kind of model would give a better performance and so on. So if there will be any questions, you can keep them for the last. I think the agenda is clear. Okay, let me start. So about machine learning, right? We all, like, there hasn't been any single field where machine learning is not there today, right? May it be infrastructure, manufacturing, economics, or e-commerce, or any industry. Everywhere there has been one or the other ML algorithm. And we all have been using this word one way or the other. But first, we would want to understand what machine learning is and how, what are the different kinds of machine learnings that we broadly classify and we broadly try to use into. So in very basic terms, machine learning is the field of AI that will help us use some kind of past data to generate some future predictions. Now we can use machine learning to get insights. We can use machine learning to do predictions, to do forecasting. This can be used for analyzing the past data, for making key business decisions by doing some statistical calculations, and it can also be used for doing some future predictions. There are multiple key facets to where machine learning can be applied in a real world scenario. We will go deep dive into the three broad categories where ML is classified today: the supervised, the unsupervised, and the reinforcement learning. Before that, machine learning, since it's been very popular for the past 5-6 years, a lot of people have this notion that this is something that has grown rapidly only in the past few years. But I just wanted to bring out the point that this is something that has been into works for a very, very long time. A lot of you might have heard about the Turing test, which was the first, you can say, building block to where people have started thinking about the notion that whether machines could think, or could machines make decisions, or could they be compared to a human mind. And from there onwards, there have been very significant building blocks into different kinds of algorithmic developments. There have been developments in the neural network section. There have been developments in the artificial ANN sections. There have been developments with different kinds of Q-learning, KNN approaches, and so on. We saw the development of RNN models, from there on, the development of LSTM models, from there on, the development of autoencoders, from there on, the development of BERT, GPT models. And today there are like so many huge complex models that are being there. You all might have heard of Chat GPT these days, which is very famous, which is based on the autoencoder GPT framework, and is being, and we can say that that is a very complex replica of how a human mind thinks, and it can actually understand and answer queries in a very real way. So this has been, machine learning has been developing block by block, algorithm by algorithm over the past few years. We would not go very deep dive into different kinds of algorithms that are being used, but we will go through different kinds of applications where these are being used, and how we can design ML problem, and how we can apply it to say one of those business use cases. I hope I'm going at the right pace. If it's too fast or too slow, do let me know. Okay. So let me first start by explaining very basically what supervised learning is. We'll start by understanding supervised learning at first. Supervised learning is nothing very complex. It's like where we already have a certain kind of data and an output with us. So we all know how machine learning in a very basic way functions, that we put in some data to it. We make sure that the model understands the data. We let in supervised learning, we let it know what the output is at first. We train those models, and we make the model understand that if A goes in as the input and B comes out as the output, then this is how the syntax or the structure is going to be. Then afterwards, we provide in some random data for it to pass it in the form of a test set, and we make it understand, we make it realize that you have learned how this works, and now you can predict for this new test set. There are different kinds of supervised learning algorithms that are being used these days. There are linear regressions, there are support vector machines, and there are decision trees. Today, in most of the business use cases, the decision tree algorithms, you would have heard of the XGBoost and the random forest algorithms. They are being used very widely in, I would say, a lot of business problems. There are time forecasting problems, there are revenue forecasting problems, there are a lot of classification problems where XGBoost and random forest algorithms are being used. Coming on to unsupervised learning algorithms, how in supervised learning, we provide it with the output as well. We say that, this data, let's say, we give it some form of images, and we also label those images, and we say, these are these images and you have to learn from this. But in unsupervised learning, we do not provide the image, basically the output at first. We allow those models to arrive at conclusions and patterns through unlabeled data. We try to cluster those data sets. We try to identify topics from those data sets, but we let the machine itself identify, what kind of data it is, rather than labeling it at first. There are various use cases where we try to figure out intent or topics. Topic labeling is a very famous use case where unsupervised learning algorithms are used. Semi-supervised learning is kind of a mix of labeled and unlabeled data. In real world scenario, it becomes very hard for us to fetch the actual labeled data, which is very clean and high quality, and that too on a large scale. So a lot of these real world problems use the semi-supervised learning, where they kind of try to generate a mix of labeled and unlabeled data, and kind of first they make the model learn on those unlabeled data, and then let the model itself label some form of its data, and then use that in the form of training to make it understand how the predictions are going to be. There is very famous generative adversarial networks, which kind of use the semi-supervised learning. These GANs are also, if today a lot of you might have read about DALE and diffusion models, where we try to generate audio and video visuals or content from text, or from very normal, let's say, video generation from images or image generation from text. These kind of problem statements use a semi-supervised learning kind of approach. and the other one, which is reinforcement learning, which is altogether a very different way of approaching to machine learning problems. This is a kind of learning through behavior, learning through trial and error. When a system of rewards is being used, we let the model understand the output, let it go into a state of active and passive behavior, and make the model itself realize whatever it is doing through positive and negative rewards. If it is going in the right direction, there are positive rewards attached to it. But if it is going in the negative direction, there are negative rewards attached to it. These kind of reinforcement learning problems are being used today in, let's say, automatic cars, where they kind of identify objects and they kind of identify the directions and they self clear their own paths and they keep on training and learning through reinforcement approaches. So these four would be very broad categories. Into a majority of these algorithms are divided. There are a bunch of machine learning algorithms that are used these days. Like for example, there will be XGBoost, random forest algorithms. There are logistic regression, linear regression algorithms. These are divided mostly into the supervised learning bucket. There are k-means, clustering, hierarchical clustering, different kinds of topic modeling, LDA. These kind of algorithms go into the unsupervised learning bucket. And even in case of deep learning, we would all have heard of different deep learning algorithms like CNNs, RNNs, LSTMs, BERT, GRU. All of these deep learning algorithms can be used both for supervised learning and unsupervised learning approaches. Okay, moving on. We'll start with very broad machine learning applications. As we already went through this, that machine learning is used in almost all the fields. I don't think there isn't a single field today where we cannot find a use case for machine learning. Some of the very broad applications I would want you guys to understand. So we'll start one by one with these applications, right? A very broad application for machine learning and specifically deep learning is speech recognition. Speech recognition is being used today in various voice assistants. We use Alexa, OK Google, and different kinds of voice assistants where they try to understand what we are saying in the form of recognizing our voice, and then they try to convert it into text and process that text to extract the intent and the question answer out of it. Various chatbots also employ the speech recognition algorithms. The ML, deep learning and ML are used in navigation problems. These Google Maps, Apple Maps, they use graph-based machine learning algorithms where they try to identify real-time mapping of the networks. They try to identify real-time traffics. They also try to navigate through shortest paths, and they use different kinds of combinations of deep learning and machine learning to get us the best possible results. This is being used in spam filters. We have a lot of emails going into spams, messages going into spams. Even if you would have seen Google Photos, they kind of identify pictures which might not be, I wouldn't say spam, but they would identify pictures which are not related to your pictures, but rather than say documents or something. So these kind of segregations that are being done, whether it's spam or not, this is being used by NLP applications. Fraud detection in the form of identifying whether a certain person is eligible for loan or not, or identifying whether a certain kind of component would lead to fraud or not. This has a lot of applications in the banking and finance sector. Stock and weather forecasting use different kinds of time series problems where we kind of employ the past data to actually predict what could be the weather or what could be the stock price for the next day or the next week. This include the time series forecasting kind of problems, and we use a lot of unsupervised algorithms here to predict what is going to happen in future. Healthcare is a very broad sector which has very different applications. And I've also pointed out a few very major applications because healthcare is something which is developing at a very fast pace. ML is being used to predict diseases, to identify diseases, to provide a personalized medicine, to have smart health records, and whatnot. There are multiple such applications in the healthcare sector itself. These RNNs and different kind of recurrent networks are being used for protein sequencing, DNA sequencing, and we are also able to identify new forms of uh, I would say DNA sequences, and basically understand and generate different kinds of content from this, which would help a lot in the healthcare improvement. Then chatbots or virtual assistants, where there are multiple use cases of machine learning. These are used in the form of intent identification, identifying what question we have, in the form of question answering, like replying with the correct context of the question, identifying entities out of our questions, like, for example, saying, I want to book a flight to Delhi at 8 p.m. So, first, it has to identify the intent out of it, it has to identify the um entities, like there has to be a flight to Delhi at a certain time period, and then it has to also perform actions on top of it. These chatbots or virtual assistants have started from a very basic dialogue flow or rasa kind of structure, but now they have moved on to very advanced forms, and ChatGPT is also one of the very advanced chatbots that we see today. Autopilot cars, we would all have heard the news of Tesla launching autopilot cars, where they employ a lot of computer vision algorithms. They use object detection algorithms. They use different kinds of reinforcement learning algorithms, where they make the model understand, how they can actually detect objects in front of them, at what distance should they detect objects in front of them, and if they do perform a mistake, or if they do not stop at a red light, then they use negative reinforcement to stop and to remember that next time they have to correct this mistake. Suggestion of products, product recommendations, movie recommendations, a lot of entertainment websites, Netflix, Amazon Prime, all of these have a lot of applications where they kind of use your past data, and they try to identify newer products, personalized products that they can recommend. Different shopping websites, Myntra, Flipkart, Amazon also use these kind of algorithms there. Social media, Facebook, Instagram, they use friend suggestions. They use these ML algorithms to provide friend suggestions. They use this to provide personalized content. Like, for example, YouTube has a lot of personalized suggestion, where if you keep watching a certain content, you would get different forms of suggestions of the relevant content that is through there. So, like, there are different and multiple industries, where machine learning can be applied. We have seen its broad application across almost all facets of industries that we can call. And the basic the best part about this is that the basic algorithms, the ML and deep learning algorithms, kind of remain the same, but there are different tweaks and variations of those algorithms that can be applied throughout these industries. So if we focus mostly on understanding deeply through how statistically and mathematically those algorithms are designed, and how we can, say, for example, understanding how a CNN kind of algorithm works, how image detection algorithms works, can have its application in multiple industries. Moving on, I would like to point out very specific applications of NLP. NLP, natural language processing, is something which is being very prevalent these days. A lot of people, it has a lot of use cases. A natural language processing is most, for people who do not know, natural language processing focuses mostly on the text. So natural language processing is basically, given certain kind of text, we can whatever the machine can understand and identify out of the text. It has its various applications in the form of sentiment analysis, review analysis. So these various kinds of sites like Amazon, Flipkart, or even the sites that we see, Go IBBO, Make My Trip, they try to identify those reviews, and they try to point out whether those reviews are positive or negative, or they extract entities out of those reviews. Like, this review is pointed about a good stay or this review is related to, let's say, good food, or let's say you're talking about a product. So over there, sentiment analysis has a lot of applications. We already saw how chatbot and email spam identification, NLP, has a broad scale of application in. Social media monitoring is something which is similar to how, these social media sites, they use this machine learning algorithms to provide personalized suggestions. Automatic summarization is being used in the form of and summarizing the meetings, summarizing the calls, and even summarizing the text documents that we have. So in order to provide us better insights out of those text documents. Language translation, like how Google Translate works, it tries to convert one form of language into another. The smart assistants, the document analyzer, and predictive text. So based, given a certain text, there can be multiple applications to how we can use machine learning models to extract information out of it. Okay. So up till now, we had gone in detail on understanding, what are the different kinds of applications where a machine learning can be seen, different industries where machine learning can be seen. And in the underneath scale, we saw that a lot of these basic algorithms involve the XGBoost, random forest, linear regression, CNN algorithms, RNN algorithms, autoencoders, LSTMs. These are the underlying algorithms that are there. I would not go through in detail on understanding what each algorithm is and how it is designed and how we work on that. But I would make you guys understand, given we already have an algorithm in place with us, how do we formulate a business problem with machine learning, and how do we decide what kind of process goes into actually productionizing that solution. So we'll go through this workflow through a certain set of example. Let's say we have an example of a face recognition system. A lot of us use smartphones today with a face ID identification, where we try to unlock our phones with a face ID. So at the backdrop of face recognition system works, where it tries to identify match your face with the one that you had registered earlier, and then give out whether it's the right user or not. So let's say we have this problem in place and we want to productionize this problem. How do we go about formulating this in the form of a business solution? So the first step that gets into processing in the for a machine learning problem is the data. It's a very common and very popular line in machine learning and AI, that garbage in, garbage out. It means that if you do not have good high quality data for you to process, you would not get proper information out of it. You can use any form of algorithm, but if the data is not good, then the output might not be as expected. So the first thing that a lot of machine learning engineers and data scientists focus on is identifying the correct data and preparing the right form of data. This involves acquiring the right set of data. So for example, we need, for a face recognition, we will try to understand the workflow through the face recognition problem. So let's say we want to do this face recognition problem. We would have to acquire a lot of data, and to acquire a lot of data based on the approaches, we would also want to understand what amount of training data do we require, test data do we require. There could also be problems like what regions of training data we require. Like, do we only have to use training data for Indians or for Asians or for Americans, for male, female, or different age groups, or different, we have to make sure that we capture all forms of humans that are going to be present in the real world scenario. Then we have to also capture data which can be different kind of races, different colors, different hairstyles. So it can actually imitate the real world scenario. Once this acquiring step is done, the next step is data preparation. This involves removing, let's say, bad quality pictures. We also try to augment the data, because a person who is going to unlock his face might be in a sleeping position, sitting position, standing position, looking sideways. So we'll have to understand that our data needs to be in different forms of augmented versions, not only one fixed version for it to work properly in a real life scenario. So this data preparation for this problem would involve, let's say, removing bad quality images, augmenting it to different directions of pictures, augmenting to different pixels, different kinds of lightings, because we might want a face recognition problem to work in case of bad lighting as well, or if we are in somewhere dark, or let's say some form of red or green lights. So we want to make sure that our data captures all form of facets of a real world scenario. Once we have all of this data prepared and properly labeled, because this is a supervised learning problem, so we would also want to label them to actual people, we go ahead with the model development task. Model development would be the first task is to identify which model do we need to use, and we can perform different kinds of experiments. We can experiment with the CNN model, with an RNN model, with autoencoders. They're like very today, so you can find very different models, different kinds of researches being done on this kind of problem, and we can segregate those models which we want to try. Then once we go ahead with the model development, we perform the training. We actually make a model run on this different kind of data. This training, because since I have picked up a deep learning problem, we would want to ensure that we do the training on high servers, like on GPUs and TPUs, rather than doing the training on CPUs. And we also want to ensure that we attain a certain level of accuracy, so that we can perform the test properly. The predictions that we do on a test set, there is another facet that involves is what kind of matrix do we want to deploy to test the data. So we can use accuracy, we can use F1, precision, recall, we can use different kinds of matrix to understand, according to our problem, which kind of metric is more reliable. Let's say for this problem, do we want to understand that identifying a face correctly is more important, or let's say identifying more faces correctly is more important? So we can have a trade-off between our precision and recall problems, and then we can go ahead with finalizing different kind of models that we had experimented with. Let's say our accuracy is not reached, right? Then we keep on validating, we keep on setting aside a validation set, testing and evaluating, and then we keep on running this loop until we reach the kind of desired performance that we want. Once we reach the kind of performance that we want, now our focus is going to be on deploying this model basically. So making sure that we test this on some real world scenarios, and we also then further monitor it or retrain it in case the data changes. If there are any questions, then we can take up in the last. So you can keep your questions together and then we can discuss all of them at the last. So there's this huge problem of data drift, like for example, in the form of face recognition problems. Once COVID hit, a lot of people had to wear masks constantly, right? So the kind of data that the model was trained on did not involve masks or covered faces or face shields. But now we want our phones to identify us even while wearing masks on. So this kind of data drift problems do occur on a regular basis. And to handle it, we would want to retrain our model, let's say with newer data, with augmented data, and we have to keep on monitoring its performance on, let's say, if our model is not performing well on a certain age group, then we have to keep on monitoring and identifying that how we can make improvements for it to perform well on different chunks of data. This is the entire workflow, machine learning workflow, that goes into productionizing one single problem. So let's say we have taken this face recognition problem and we have understood how we progress ahead with first to like from acquiring the data to actually productionizing the model and retraining and this entire process. But how do we do it in the real world? So next we are going to learn on how it is actually done today and what kind of tools do we use today to do this in different companies. Okay. So we'll read about MLOps. MLOps is basically how, with different software engineering problems, there are DevOps kind of standard practices. MLOps is basically machine learning engineering standard practices and the kind of process which streamlines this task of developing a model, productionizing it, maintaining it, and monitoring it. Only taking in the data, developing a model is not sufficient when it comes to actually applied machine learning, because we would want the model to go ahead into production and to maintain that form of accuracy that we had reached earlier while training. And that necessarily doesn't happen on real world scenario all the times. There's a high plausibility that our real time data differs from our training set and our model kind of stops performing well. So we have to keep on maintaining different versions of models, different forms of experiments, and we have to keep on tracking them. So these MLOps principles are deployed across the kind of data analysis processes that we do. So these now this all of this we discussed for one single problem, but there could be multiple problems that a company is working on. Let's say along with face recognition, the company can also be working on email detection, right? So there could be, or the company can also be working on a different form of image detection. So there can be similar EDA practices that can be used across projects. But if these are not tracked properly, we cannot actually use these practices or standard algorithms for different projects altogether. So MLOps will standardize this entire structure. This will help us identify different forms of EDA, different forms of feature engineering tools, different forms of model training, tuning, the review of model of whether a model is performing well or not, how we are inferencing it, how do we want to monitor it, and then if we want to retrain it on a different test set. There also comes the question, let's say we want to deploy the face recognition problem on our phones. Then along with maintaining accuracy, another problem statement that comes up is to identify the latency of the CPU server, right? Because you don't want your phone to just be in front of you and wait for 5 minutes for it to detect your face. You would want it to identify your face within seconds. So your machine learning or deep learning algorithm has to actually identify your face or whatever problem, has to predict the answer within seconds. So we want to also ensure that a CPU latency is maintained along with ensuring a high accuracy. To track all of this, machine learning operations are used these days, and we'll go through one such MLOps that is being used. And then there are like multiple different tools and companies offering this. You can read about them and try to pick up any one of them for your problems. Today, we'll go through MLFlow, which is provided by Databricks. Databricks is a company that provides the entire structure or the entire pipeline for training, deploying, maintaining, data ingesting, and understanding the entire workflow. So this MLFlow has MLFlow tracking, MLFlow models, MLFlow registry, and MLFlow survey. All of these different sections have different kind of tasks. So for example, MLFlow model mostly focuses on logging a given model. Let's say you're trying on multiple experiments. You're trying on XGBoost, logistic regression, or naive Bayes classifier, or 3-4 different kinds of classification problems together, and you would want to get their results together and you're also trying to perform different kinds of hyperparameter optimization on top of it, and you would want to ensure that all of this gets tracked properly for you to take a final call on which one to go ahead with. This kind of tracking of the models before and after deployment is done by an MLflow models. MLflow registry enables you to version these existing models, transition them from staging to production. So let's say you have multiple versions of a given model and you want to keep on improving it month by month or day by day, and you want to test the entire server by converting it to API endpoints, and then you want to take it to production. So this entire pipeline is achieved by this MLflow registry, serving, and models. We will go through one very basic tutorial on how we can use MLflow to track and to productionize a very small problem. And then you can go in detail to understand that how you can use it for very complex use cases as well. Okay. So there are multiple machine learning tools that are used these days for different kinds of, I would say, different sections of machine learning problems. So this is just a very broad overview of, different languages being used. We use R, Python, Julia, and, different forms of languages. There are different data platforms for data ingestion. So Apache Spark, PostgreSQL, different kinds of SQL servers. They allow you to track big data, millions and millions of rows, perform different kinds of experiments on it. So Apache Spark and PySpark can allow you to perform different kinds of, let's say, filtering in feature engineering kind of tools on that huge amount of data that you have. Then there are different ML and AI tools like TensorFlow, PyTorch, which we can actually use to write the machine learning modeling code. There are different data exploration and visualization tools. Excel is a very basic tool to understand and visualize the results. But like, for example, in Python, we use matplotlib and different kinds of visualization techniques to understand the data. There are different data ingestion tools, which we use to input the data into our system on a regular basis. So let's say up till now, we have discussed on how we will proceed ahead with training a model. But once the training is done, once we have the model, once the model is live in production, when you want to do a real-time, day-to-day basis, so for example, you every second you would want faces to come into your model, and you would want it to recognize, and you would want it to launch the output of whether it matches the face or not to a given user. You would want a real-time data ingestion platform which can keep on giving it, the inputs through an API and keep on launching the outputs and releasing it to the clients basically. And there are different development tools in the backend. There are Jupyter notebooks, there are Visual Studio, which provide you with enhanced capabilities on applying different forms of machine learning algorithms. So this is just a very broad overview of how we can use these different kinds of tools today in order to make sure that we can easily productionize different chunks, and then we can bring them all together to convert one machine learning problem into an actual revenue bringing business use case. Okay, let's go through various challenges that are there in deploying machine learning. So we'll go through very slowly through all of these challenges because these are very important challenges that we face today. Taking in that certain data and training a model, identifying the right model is a very basic challenge, right? But what happens when, let's say, you do not get the kind of desired result that you want, or we are not even sure what kind of results do we expect from the model? At a production level use case, there are multiple challenges that come up, not only involving model training, but different forms or different chunks of that process. So let's say our first problem would be to choose the right production requirements. So let's say we have a Netflix recommendation problem, right? We would want our model. How Netflix recommendation problem works is, let's say you watch, if you're a newbie, you choose 5 or 6 pictures or let's say series of your choice. And then the model will try to start recommending personalized content based on the things that you start watching. Now, the right production requirements would involve identifying first, because you would not want to make it very biased. Let's say you picked one horror movie and one comedy and one, let's say, a documentary. Then you would not want your entire page to be filled with horror stuff. You would want it to be personalized, but also diverse, because then you will be able to explore and know the content in a better way. You would also want a real-time latency. You would want to ensure that, so let's say you don't want that every 5 minutes your model, your recommendations keep on changing, because the user would want to actually give some time to understand, how whatever recommendations are being provided, and want to go through them and want to also wish list some, or let's say like some of those content. So basically the first problem comes in understanding what are we expecting from our machine learning problem? What kind of, let's say, results are we expecting? Do we want to prioritize mostly on the accuracy, or do we want to prioritize on making a lightweight model which can be slightly less accurate but faster? So these kind of right production requirements, if these are clarified, then a lot of problem gets solved because you know what you're targeting first. The second problem comes in lack of standard tools to deploy machine learning. So we have with MLOps, this has kind of improved a lot, but still a lot of machine learning problems do not use MLOps or MLFlow to very regularly track. We keep on experimenting with different versions, different models, different forms of data sets. But since those experiments, as they keep on becoming more and more and more, the entire tracking and basically making sure that those experiments can be replicated, that becomes very difficult. So let's say we finalize a certain set of hyperparameters and we kind of go ahead with them, then the entire tracking process for it to actually get replicated becomes difficult. Another challenge that comes up with the offline deployment. So let's say we thought about deploying the face recognition algorithm onto the phone itself. Now, running a machine learning model on a GPU or on a server becomes comparatively easier because you have a huge CPU bandwidth for you to run your models on. But if you want to run it on phones, or if you want to run it on, say, watches, they have a very limited bandwidth of CPU memory and also CPU usage because they run on a different kind of servers. So those kind of deployment problems also come up when we target real-time deployment scenarios. Identifying the correct metrics to focus on, like for example, in case of healthcare problems, identifying whether a person has a certain heart disease or not, we would want to 110% ensure that we do not predict the wrong results. It's okay to not predict if a person, even though a person has a heart disease, but it's not okay to predict the wrong results, or vice versa, based on whatever that company targets. So, identifying the correct trade off between precision and recall problems and identifying which to focus on is very important. Considering the data drift and model scaling. So let's say we want to run this facial recognition problem for thousands of people. Now, in a year-long span, we want to scale it to hundreds and thousands of people. So introducing this huge training set, introducing a real-time model running, scaling this to a broader scale becomes another kind of machine learning design problem which we need to solve. So these are the various challenges that we face. There are like a lot more challenges that come up, but on a broad scale, these are the challenges that we face while deploying machine learning problems. Okay. So the first hands-on tutorial that we'll go through is to understand how MLFlow. We have learned about how MLFlow can be used to track, monitor, and deploy the entire machine learning problem, starting from data ingestion to model deployment. And now we'll go through the entire tutorial on considering one single data set and one single problem on how we can actually do this using MLFlow. So MLFlow is part of Databricks and they have launched this open source tutorial. So the data that we'll be using is this wine quality identification. This is from the UCI ML repository. This is a very famous data set that's being used in different Kaggle competitions as well. So the data is basically to identify the wine quality. And there are various features. The goal is to model the wine quality based on physiochemical tests. And we will be using, so along with how we do a model deployment on our notebooks and everything, few advantages that are, we'll be pointing out a few advantages that are there using MLFlow. We will be, it provides an easy capability of using hyperparameters while on the go, rather than building one model first and then using some kind of grid search or something to, experiment with different hyperparameters. We can actually, during the training process, introduce the hyperparameter selection for us to get the best model in the first place. Along with that, it provides us easy tracking capabilities. So we'll just go through this tutorial very quickly to identify how we can train the model, how we can compare the different models that are formed, what kind of requirements are there, and how we can deploy this model. So for this, basically, few very required dependencies would include MLFlow as well as scikit-learn. This entire tutorial would be in Python language. So if you're not comfortable with Python, just understand this and then we can go in deeper detail. It's not very clear. We can it allows us to install Conda, and then once Conda is installed, then we'll be installing MLFlow and scikit-learn for us to run these packages in the front end. They have an option of running this entire flow in R as well. I'll be going through the Python version for now because it is more widely used. So since this is a linear regression model, it allows us to take two hyperparameters, the alpha and the L1 ratio, for us to train on, basically. So how a lot of you who would have actually trained the linear regression model at least once, the difference that you can feel along with, rather than just a normal training is we will be allowed to introduce hyperparameters on the go, and we will also be allowed to log these metrics on the go. So while importing the MLFlow, okay, let me just show you the flow. Yeah. So the flow would include for us to actually read the actual data set, for us to split the data set into a train and test set, for us to drop the output value, the quality value, which we want to predict from these. And we can decide the alpha value based on a certain threshold limits. And we can decide the L1 ratio as well. Now we track it using MLFlow.startRun. We try to introduce MLFlow into this, and we try to fit the model by introducing alpha and L1 ratio into this. Once we get the predicted values, we generate the evaluation matrix, the RMSE, mean error, and R2 value. And then we try to basically go on a loss convergence and log all of these parameters. So we log the matrix and we also log the params that we tried on. Once we track these experiments, we log the model as well for us. So for example, through a permutation combination, let's say we get 25 different versions of, different hyperparameters, different outputs, different models. It allows us to log all those models together. So once we go through the results, then we can just pick the model ID of that model and go ahead with finalizing. So this example using the pandas, NumPy, and sklearn API to create a simple machine learning model. And we can run this with the default hyperparameters as well. It does not necessarily, we do not need to train those hyperparams. I'll just go through how we can compare these models. So how we can use the MLFlow UI to compare the models that we have produced. So once this is trained, it comes out in this format. Okay. So if you can just see this particular structure, this involves the date on which it has the date and time, the user, the source will be the notebook that has been used to train, the version, and the different parameters and the different metrics. Once we have received this, we can actually finalizing using these metrics that we have. So we can, so for example, we can decide on which metric to give a higher importance to, and then based on wherever we are getting better results, we can finalize, let's say this particular model, if you want to go ahead, or this particular model, if you want to go ahead, then we can identify this version of the model and then track it. We can also use the search feature and filter out. So for example, we can query that we want RMSE to be less than 0.8, and it is going to eliminate all the values which have a value of more than 0.8. Now, packaging this code together, this is just one basic version of tracking, right? Instead of using one single model, we can go ahead and experiment with multiple models because this is going to be in one particular notebook. We can go ahead and experiment with different forms of data set as well. We can track all of this together. Once we package all of this, we can use MLFlow projects together. We can specify the dependency. So this is basically trying to run it in a Conda environment, because running it in a notebook and then running it in future for a proper production level environment. So we design a Conda level environment for this. And then we can replicate this experiment by introducing MLFlow run, this experiment that we had created, by giving a certain value. Once we run this kind of experiment gets replicated. We can also specify a certain specific pip requirements that we need for this. Okay. So now we are trying to load on different data sets. So let's say, okay, this example demonstrates how to specify PEP requirements and then also log in a different data set. So we have loaded the iris flower detection data set, and we are trying to try with the XGBoost model for now. So we are going to log this XGBoost model, get the specific requirements which are required for a certain XGBoost model, and then we are going to train that particular model. Once we do this, we can also serve this model. So let's say we have finalized which kind of model we want to go ahead with this. We can do a real-time REST API kind of serving. So after logging this model, we'll have the run ID for that particular model. Given we finalize these params and these metrics, we have its path, full path available with us. So once we have this full path available with us, we can either download this, or we can use this particular path itself to serve this. And to deploy this on a server, we use the MLFlow models API, and then we run it on an API. So now what can happen is we can pass on the data, and we can run the predict function through an API where it can keep on generating and serving predictions to us. This is one very basic tutorial on how we can track these experiments, how we can deploy these the finally logged models, how we can try with multiple kinds of hyperparameters, multiple kinds of data sets, multiple kinds of models together. And this entire process gets such streamlined. This can also be done in a different language. And all of this gets tracked at a single location. So we need not go back and look into different kinds of so like a lot of people face this problem where they have different Python files or different notebooks for different kinds of experiments, and then they lose a track of which was the final version. So this also keeps the version track together, and this can be easily linked to your GitHub repo or wherever you want to place your final code. So here we saw how we can efficiently track these models. I just want to go through another hands-on tutorial, which will not be this MLFlow tracking, but that tutorial will be on one's NLP problem, where we want to understand on how we have actually progressed on the NLP front. So we learned about NLP having various kinds of use cases in identifying the text sentiments or the text spams, but over the period of years, how we have progressed and what kind of, so basically we want to cover different kinds of approaches that we can go ahead and try on a certain text problem. It's not always necessary that let's say it's a sentiment problem, then let's just bring in autoencoders at first and let's just go ahead with this. They can have good results because they are proven to have better results on a lot of different data sets, but it's always recommended to start with very basic building blocks first, understanding your data first, and then step by step improving your model complexity so that it becomes understandable on where the model fails. Because if you try to just implement the latest, most complex version in the beginning itself, it will become very difficult for you to understand where your model is going to fail, because it will act like a black box. So it's very crucial to go on a step-by-step process. So okay, 1 second. So the way we saw, we have different steps in a machine learning workflow. We have a data acquisition, a data preparation, a model development, a training, different kind of steps there. So for each of this step, it is very important to spend some time and, not just skip one step. Let's say we have gotten the data, we'll just use the latest autoencoded model and we'll eliminate the exploration or feature engineering part. Then also there's a high possibility that it won't work. So we'll go step by step in understanding and approaching one NLP problem. We'll try to understand what different kinds of EDA can be done on it, different kinds of approaches that can be tried on it, from very simple to very complex, and different kind of models that can be implemented. Okay. Yeah. Okay. So this is a Kaggle problem, very basic Kaggle problem, but this same kind of concept can be applied to a real world production problem as well. The problem that we are going to target today is a text classification problem. This is a Twitter disaster tweet classification problem. we want to identify whether the tweet is a disaster tweet as well, disaster tweet or not, basically. So you can consider this in the form of a binary classification problem, similar to different kinds of text classification problems like review classification or sentiment classification. So NLP has its applications in different kinds of retrieval, answering, extraction kind of problems. So the flow that we'll go through is, we'll first go through the EDA on what things can be tried on a text data set. We'll go through with different kinds of data processing techniques, how we can clean the data, how we can identify the output labels, clear our data, different kinds of token visualizations, because since it's a text data and we know that machine learning takes input in the form of numbers, so the kind of ways we can convert this text into numbers, then different kinds of models that we can use, ranging from very simple XGBoost machine learning models to LSTM models to BERT models. And then we'll go ahead and combining this entirely together. Okay. So we are using different kinds of data sets here. One, we'll start with the spam collection data set. So this, the data is of the form that you have messages there, and your target is either it's a spam or it's not a spam, basically. So the kind of EDA, we'll start with identifying what kind of EDA techniques we can apply on. So one basic EDA is to identify whether a data set is balanced or not. This is a very underrated step, I would say. Identifying your data, because in real world scenario, there will be 90% of the time you will not get a balanced data set. And most of the algorithms that we are taught, or the way we design those algorithms, are based on balanced data sets. So then it becomes a huge data drift from what is expected to what we run. So it becomes very important and crucial for us to identify whether our data is an imbalanced data set or a balanced data set. So for example, in case of spam or not spam, majority of the emails that you would be getting would not be spam, basically. The ratio of spam emails would be very less. So considering this as an imbalanced data set problem, how we can change our modeling techniques for it to map to an imbalanced class problem. Okay. So once they did the data distribution by target, they identified that spam was only 747, while not spam was majority of the data, 4825 out of 5,000. And they saw that the classes are imbalanced, so they considered some kind of resampling, basically. They also identified data roles in different fields, considering what was the message length, to figure out whether spam messages have a identifying it as a form of feature. Let's say if spam messages have a larger length, so this can act as a feature that messages with, say, more than 100 tokens could be classified into spam. So they identified a you can say a distribution where they saw that majority of the emails which were not spam ranged of length 5 to 6 units, versus majority of the emails that were spam were in the range 27 to 30. Now, data pre-processing and data cleaning. These two are very basic steps that we apply on a text form of data set. We apply different form of regex. Regex is something that is widely used in NLP problems. You can go through regex cheat sheets and regex problems, which are used to identify patterns out of a text and clean those patterns from the text itself. So we identify different kind of special characters, emails, basically HTTP marks. We identify different kinds of not alphabetical words, and we clean our data. So for example, the first example that we see, it converts it into lowercase. It removes these special dotted lines, spaces, and it makes it very clear. We can remove the emojis as well, because emails might contain all of these text informations. The next step involves stop word removal. Stop words include, so we can have sample stop words as well, but the NLTK stop word corpus includes the words which are very commonly come into a sentence. For example, the prepositions and, are, the, is, Those kind of words which do not have any contextual meaning, but they are so frequent that the model can get biased because of their occurrence. So we try to remove those stop words, the English stop words from the text. Then we try to stem or lemmatize the data. The reason for stemming or lemmatization is to ensure that words with similar meanings are considered together. So for example, cleaned or cleaning or cleans, these come from the basic stem word called clean, but they can be used in different sentences in different tense, past, present, future tense, and different forms of verbs. So we try to stem and lemmatize it to make sure that we get the base word together and the context remains the same for different kinds of words. There are different stemming algorithms that they have tried, Porter stemming, Lancaster stemming, that you can go through and identify. Bringing it all together, they have cleaned their data, converted it into lowercase, then stemmed it, removed stop words, and gotten clear tokens out of it. Now they've converted their output in the form of label encodings. Why label encoding? Because we do not have it in the form of 0, 1. We have it in the form of text as well. So we convert the output text into numbers and then converting basically converting our text into tokens. Now, when they identified the top words, so the ham messages are the one which are not spam basically. So when they identified the top words for ham, it involved got, go, come, okay. So this is done using a word cloud. We can use in Python, we can use word cloud to identify or based on frequency, understand which are the top words that are being used and the top words for spam. So as you see, the top words for spam involve price, cash, cost, free, call, something which is very much related to a phone or a incentive kind of words. Now the next comes in the form of vectorizing. We want to convert our tokens to numbers, which is a very important task. That different kinds of techniques that we can use for vectorizing. We can use a count vectorizer, which just counts the occurrence and converts these tokens in considering making a vocabulary, converts these into tokens. And then they try to split the data into training and testing and fitting it basically on the train set. There's also tuning of this count vectorizer. I'm not going very much deep into this because I want you to understand on what different techniques we can use. And then for each of these techniques, we can go ahead later in a very deeper way and understand this. There are TF-IDF tools which are used basically. I just want you to understand the flow that starting from very basic label encoding, count vectorizing to TF-IDF to using BERT, how we have progressed on just the same data set. TF-IDF is term frequency, inverse document frequency. This is basically a number that we identify for each of the token, which comes in the form of number of times. So, okay, so this is a multiplication of its TF number into its IDF number. So for each word, the number of time a term appears in a document, and then inverse document frequency is the number of times, basically the number of times that word comes across all the documents. So once this comes with us, we identify the TF-IDF number or a TF-IDF ratio for each of the number. And then based on that, we convert our input tokens into numeric form. From advancing from this TF-IDF comes word embeddings, the GLOVE word embeddings. Similar to GLOVE, they are word-to-vec word embeddings. I'll not go through into detail, but GLOVE and word-to-vec word embeddings actually use a 300 dimension or a 400 dimension numeric embedding, or you can say a numeric vector for each word. And then they try to concatenate this together for a sentence. So for example, this is a sample. Once you tokenize this, for each, there's a corpus or a dictionary where for each word, the vector is saved. So in the final run, you can just concatenate the vectors for each of these words and you can get the vector for this entire sentence together. We pad the sequences for us to get a single length, basically the same length token, because the text could be of different lengths. And then we identify the glove embeddings for each of these. So this is the embedding 100 dimension. This glove 6 billion 100 dimension TXT is a glove corpus. We can find this corpus online. And then this acts in the form of a dictionary. We just search through this dictionary for that particular word and extract its embedding. This was different kinds of techniques, TF-IDF, glove, similar to glove, they exist a word-to-vec embedding, or you can do a count vectorizer, you can do different kinds of EDA, data cleaning, to convert your clean text into numbers. Now, we can use this numeric data to model by using different kinds of models. So how earlier we saw that using MLFlow, we can run a logistic or a linear regression model on a given data set. We can run a XGBoost model on a given data set. We can also try different forms of models. So for example, they have tried to fit their data on a multinomial naive Bayes model. And then they have tried to also fit their data. Okay. So on a multinomial naive Bayes model, they have run the confusion matrix. They have tried to identify the true positive, false positive values, and they've tried to generate the accuracy out of it. So they've received a 0.978 accuracy. But we know that accuracy will not be a clear comparison, because accuracy is only the right metric if the data is balanced. If the data is imbalanced, one should always go for an F1 or another metric, because accuracy would not give you a clear description of whether your model is performing right or not. So then they generated the AUC value for this, which is a better comparison when it comes to imbalanced data sets. Next, they tried to run this using this entire pipeline of a count vectorizer, TF-IDF, and a multinomial naive Bayes. And again, ran the confusion matrix through it. Now, instead of a multinomial naive Bayes, we introduce a XGBoost classifier with a certain set of hyperparameters. And these set of hyperparameters can be further tuned if we try to introduce MLFlow into this pipeline. So once we fit this, we see that on the train set, we receive an accuracy of 0.98, and on the test set, 0.96. On improvement over the XGBoost model, they've tried with introducing an LSTM, which is a deep learning model, where they have run a sequential model and introduced the embedding, the glove embedding in the form of an input dimension. And they've added a bidirectional LSTM on top of it. So this entire sequential model includes this max pooling layer, batch normalization, dropout, then a bunch of dense and dropout layers, and then compiled together. Once they have the sequential model with them and they have the input embeddings with them, they try to run the model, and then they see the results over the loss and the accuracy. Over this confusion matrix, okay. So over this confusion matrix, on the test set, they have seen an accuracy of close to 0.98. But on the test set that they have, the validation set, they see their accuracy dropping basically after a certain set of epochs. Then they try to introduce BERT into this. So I'm not going to go in deeper details as to what BERT is, but on a very broad scale, BERT includes transformers. So it's basically an encoder representation of transformers, which are being used to rationalize, or basically these have changed how we look at text. This is BERT will then replace all of the process. We just clean our data. Instead of using a glove, word-to-vec, or a TF-IDF value, we directly convert text into BERT embeddings, and we use those BERT embeddings for a sequence classification problem. So, okay. So they use a word piece tokenizer, a BERT tokenizer, rather than using a count vectorizer or something, like a basic split by space kind of thing. They use a BERT tokenizer. And once using a BERT tokenizer, they get their tokens. They generate the embeddings out of BERT encode, will generate the embeddings and masks for those tokens. And once they do this, they use an ADAM optimizer and sequential model in order to train a BERT model, basically. So we train a TF BERT model from this, and we generate the predictions. So, okay. So this model will have a shape in the form of an input layer, a BERT model, a dense layer, and a dropout layer. This dense layer is a cross entropy layer. which will give output in the form of 0, 1, whether a certain text is a spam or not. On fitting this BERT model, we see that the validation accuracy has also improved. Like earlier, we saw that the validation accuracy was 0.96. This has improved to 0.98. And then the training accuracy has gone up to 0.99. And with the LSTM curve, we saw that the test accuracy was dropping. But with BERT, we saw that even the test accuracy is improving. They have replicated this similar kind of experimentation, So we saw how we have progressed on top of it, right? From scratch, from using TF-IDF to GLOVE to Word2Vec, introducing this entire pipeline with the XGBoost model, converting this XGBoost model into an LSTM model, removing this entire pipeline, cleaning the data, introducing BERT embeddings using a BERT model. This entire workflow can be replicated on another set of problem statement, which is a similar text classification problem. So they've tried to replicate this on a similar disaster tweet prediction problem, doing again dataset distribution. Now here, this is a more balanced data basically, whether it's a disaster or not, this is more balanced. And then identifying data roles in different fields, the length of the text, that whether it's a certain disaster or not, pre-processing it, removing these emojis, removing stop words, stemming it, lemmatizing it, identifying its word cloud, identifying what are the top words which are used in a disaster tweet and which are not used in a disaster tweet, and then modeling it basically. So modeling with different experiments, modeling with the XGBoost classifier using TF-IDF and count vectorizer, generating its confusion matrix, modeling with a GLOVE LSTM approach. Okay. And then, 1 second. Yeah. So with a GLOVE LSTM approach on training multiple epochs, we get a validation accuracy close to 0.80. And then again, trying with the, okay, which is this? Yeah. So this, we get an accuracy of 0.80 with a GLOVE LSTM approach. And then with an XGBoost level model, yeah, we get an test accuracy of 0.77. So we saw that using how GLOVE and LSTM, there was an improvement on top of this pipeline of TF-IDF and XGBoost classifier. So with this, we can see how we have evolved in the NLP domain. We keep on trying, with basic forms of tokenizing and converting into basic form of embeddings, GLOVE and Word2Vec embeddings. Then since those word embeddings were not capturing the entire context, there have been improvements in BERT embeddings, which are way better in identifying what a word represents. Then along with those BERT embeddings, rather than using recurrent neural networks, we go one step ahead. We use a stack of those recurrent neural networks in the form of encoders, decoder network. We use BERT, and along with this, since they have tried BERT, they can be multiple things. They can try GPT models and a lot more, like the list keeps on going. So this is how the NLP has progressed over the years. And when we also face similar kind of text classification problems, we can try multiple such experiments to see what works for us and what doesn't work for us.